So as you may have guessed, looking at the timestamps on these videos, they're all recorded different times, different months, different years. You can tell by the changing shirts. A lot goes on between videos. And I did a video on KAQ a while ago, and it is a long video, and I like the video, but there is something wrong with it. And it's a huge chunk of the video, and I have no wants or desires to go back through and correct it. So this is a special video to correct the video on KAQ because I really don't feel like remaking the KAQ video. So in my KAQ video, I talk a lot about what an equilibrium constant is, and I say KAQ equals this really complicated function of activities and concentrations. And that's true, but it's only true at equilibrium. So we have a special term in chemistry, and this is what's called the reaction quotient, Q. Now Q is a function of concentrations and activities. Now at equilibrium, we have the statement KQ equals Q. And this is true and only true at equilibrium. So at equilibrium, we can definitively say that whatever this equals numerically is also going to have to equal numerically KQ. The reason we had to break it into two parts, though, is that KQ is a number. And it's set by a physical constant, set by the free energy change, delta G naught. Q here is a function. Specifically, it is a function of concentrations and activities. So the full expression for Q, which in this video I say is a full expression for KQ, is that Q equals the product of the concentration of the products over their activities raised to the reaction coefficients divided by the reactants. Specifically, the reactant concentrations divided by their activities raised to the reaction coefficients. So it is products of reactants, and this is a function. We will get a mathematical expression that we may or may not have values for. Now, there are a few things about Q we have to know. First of all, these alpha terms here. Alpha is defined as the activity of the phase. So basically, it describes energy, and it's a reference state. Now, the reference state is always going to be room temperature and 1 atmosphere, but alpha is going to take on two different values depending on what we're working with. So if we're working with solutions, something that has an AQ or gases, alpha is going to equal 1 molar. So our reference condition is 1 molar of whatever it is. Because of that, alpha never appears in our expression for Q. If we have a solid or a liquid, alpha is the density or concentration of the solid or liquid. And the reason we make this definition is that it makes the concentrations divide out. Now, the idea here is that if we have a solid or liquid, unless we go to extreme temperatures and extreme pressures, we're not going to change their concentrations. And that's what's driving partitioning with equilibrium, is if you can change the concentrations. Solids and liquids don't change their concentrations, and so they disappear from our equilibrium expression. Our VI's here are new I's, not V's, but they are news, are the reaction coefficients. They basically describe, if you look at the reaction, the numbers beside the reactants and products. So, ultimately what this will do is twofold. One, by dividing by the activities, we end up canceling out the concentrations of the solids and liquids, and we leave ourselves with the gases and the aqueous mixtures. The other thing is that it gets rid of the units. These are all units of molarity, and so Q here is unitless, as is KEQ. It doesn't look like it when we look at the expression for Q, but it is because the activities disappear. And in case you don't know, pi here's the product. So how do you find Q practically? Well, there is a shortcut method for finding Q, particularly if you don't really want to work through all this. Now, I caution against the shortcut method, and I caution against it because it glosses over a lot of details, but you can still use it. Just realize that this is what's actually going on. Let's say for the moment you have the reaction of nitrogen gas plus hydrogen gas going back and forth to liquid ammonia. So N2 plus 3H2 goes back and forth to 2NH3. What is the expression for Q? Well, we can use this big nasty equation, or what we can do much more simply is we can write out the product concentrations, in this case NH3, this bracket I here, raised to the reaction coefficient 2. And since I don't have more products, I'm done with the top. For the denominator, the reactants, I'm going to write out the concentration of the reactants And these are all molarities, and raise each of them to the reaction coefficient. So nitrogen to the first, and hydrogen to the third. So this is my product, my pi's, my concentrations, and my nus. Now, what my activity will do is it will make the concentration of any liquid or any solid equal to 1, because I'm going to divide by its concentration at room temperature in 1 atmosphere. So since I have NH3 as a liquid, this is going to end up being 1 squared, or just 1. I'm dividing the concentration of the N2 by its activity, which is going to be 1 because it's a gas, so I end up with just the concentration of N2. And I'm going to divide the concentration of H2 by its activity, which is 1 because it's a gas, and this will leave me with this expression. Q equals 1 over the concentration of N2 times the concentration of H3 cubed. Now, doesn't look like it's unitless, but it really is, because we're dividing by activity. It just happens to be the activity is 1, so it disappears from the equation. But this is how you find Q for any reaction. Now, if we had NH3 solid for whatever reason, that would also disappear. So when it comes to your expressions for Q, you shouldn't have anything that is a solid or liquid phase in your final expression for Q. Now, practically, how do you use this? Well, the first step is finding Q. When we go to later videos, we're actually going to put in concentrations for these gases, or aqueous mixtures, and they're going to tell us basically how things are partitioning, and we can use these to find things like basically changes in free energy changes in delta G. So, again, I've got another video on KAQ. I talk about this again, probably a better video than this, but full disclosure, that video is actually wrong. KAQ does not equal this expression. KAQ equals Q at equilibrium, and this is actually the expression for Q.